Moving to the next contaminant that we can have in solution, and it is metal contamination. Metal contamination in aqueous media is best described by what is known as a Pourbet diagram. Now, a Pourbet diagram is for a certain species, so calcium in this case, describing the presence of that species as a function of the pH and as a function of the potential of the solution, so the PE. And depending on the pH of the solution and depending on the oxidizing power of a solution, a species will be present in a different chemical format. They can be present, in the case of calcium, as a doubly charged ion, but they can also be present at high pH as a hydroxylated species. Or at high oxidizing power, they can basically be present as calcium oxide particles. So, but with this, you can already see that by playing with the pH and by playing with the oxidizing power, we do have tools available to control how ionic metallic contamination behaves in solution. What is important to know is that for metallic contamination, as a rule of thumb, you will have good solubility at low pH. So there's a tendency for metallic contamination to be removed from the surface if you work at low pH. There's a high risk of forming hydroxide species, insoluble species which will absorb on the surface. So for metallic contamination, moving away from high pH is beneficial, remaining at low pH, remaining at low pH is beneficial, working at high pH is detrimental. High pH, there is a high risk that metallic species will go on the surface. I forgot to mention one thing, that for the particle removal, the opposite is true. So for particle removal, the etching of a surface happens better at high pH. So if you have high pH, you will have more surface etching. And you already see the contradiction here. For a particle removal, we prefer high pH. For metal contamination, we prefer low pH. So there's the constant debate or the constant dilemma on how to work with the cleaning solutions. And there's no tailored solution that will solve all the problems. You will have to design it based on the process under consideration. Now there's one thing that I did not specify is the oxidation potential of a solution. By adding oxidizing or reducing components to the cleaning solution, we may also have a plating, so a redox couple being formed, and the risk that contamination basically, instead of absorbing on the surface, plates on the surface, so that it forms a metallic residue on the surface. And that is one thing that we need to take into consideration as well. When is that reducing activity or the metal plating becoming a concern? Well, it becomes a concern when we have a hydrogenated surface. So going back to one of the first slides, a silicon surface that is hydrogen terminated is very likely to undergo a reduction reaction of metallic ions in solution because of the fact that the silicon can become oxidized. So the silicon becomes oxidized and the metal ions, the ones that are more noble than silicon, will become reduced. And we will introduce copper metallic contamination on the surface. So we'll have to reverse that process using an oxidizing chemistry to remove the particles, the metal contamination from the surface again. This type of process here is extremely riskful when we work with a hydrofluoric acid solution. Anybody an idea on why that would be the case?
Fluorine has a high affinity for silicon.
It has high affinity. HF actually will dissolve the oxide, so it etches the oxide. Now, if it etches the oxide, then you basically keep the engine running, because you can again oxidize the silicon, plate the metal, and then the oxide is etched again. So in HF solutions, you will not only have a hydrogenated surface, but you will maintain a hydrogenated surface because of the fact that the HF is etching the oxide and the noble metals can plate out. The non-noble metals are not a concern in this particular case. But keep in mind, metallic contamination on an oxide-free surface, be aware when you have to deal with noble metals. Is a hydroxylated surface, so a surface where we have OH groups, is that fine? Unfortunately not. In order to explain this, we just have to go back to the fact that an OH terminated surface, the OH groups are behaving as weak acids. So basically, we can write this equation here, so that the OH terminated surface can lose a proton and can form a dehydroxylated charged surface site. On this surface site, a metal ion can absorb, and the metal ion basically becomes chemisorbed on the surface through an SiO-M type of bond. That's, I hope, obvious from these two equations. Now, the total amount of surface sites on a surface of a silicon wafer, they're either either protonated or they have a metal ion absorbed on that. And then depending on the pH, you also may have some deprotonated surface sites. But the total amount of surface sites is limited, and it's in the order of 10 to the 13th surface sites that you would have available on a surface. So that means that you can theoretically absorb up to 10 to the 13th atoms of metal ionic species on these hydroxylated surfaces through that exchange reaction. Now you can rewrite the equation here, and then you basically come up with the conclusion that the number of sites that are occupied by a metal ion are proportional to the total amount of surface sites, logically, and are inversely proportional to the pH, and, well, most important, inversely proportional to the pH. So we can already see that if we have a high acidic solution, we have high proton concentration, and we will have very low metal contamination on the surface. And that is what you see expressed in this graph here. So you have the calcium 2 plus concentration in solution, and we have the surface concentration of calcium measured on a wafer. And you can see that there's a drastic drop-off, obviously, with the metal concentration, but there's also a strong dependency on the pH. At low pH, we have less surface size than at high pH. So again, this is where low pH is beneficial. And this slide is comparable to the slide that I showed on the particle removal. You have the chromium concentration in this case on a wafer, and as a function of the removed oxide layer. So also here, etching will also help you in reducing the surface concentration apart from the pH effect. Now, there's some points here in this corner here, and in this case, we talk about chelating agents. So one trick that is often done when we're working at high pH solutions, which is in this case happening, we would have at high pH theoretically a lot of surface sites occupied by a metal ion. But if we can take the metal ions that are in solution, if we can sort of neutralize them by forming a chelate complex, so by basically having them interact with EDTA, for example, then they are not part of the equation anymore and they will not contaminate the surface. So you can also play on the chemistry side. Once they are released from the surface, then you can basically complex the metallic ions and keep them in solution. So basically play with the diffusion and the removal process, the two other terms in the cleaning equation that I showed earlier.